We will continue our discussion. We will start with an example on work energy principle, and then that will be the last example we will be doing, and then we will move on to impulse momentum principle. We will define the term impulse, we will talk what is the impulse momentum principle, and we will see how this leads to the concept of conservation of linear momentum. So, that is what we will do in today's class. We start with another example. What we are given is that there is a table on the end of which there is a pulley, and on the pulley through a string two masses A and B are connected. So, blocks A and B are connected by a light cable on a frictionless pulley, and the pulley is also very light. That means we can assume this is massless. This is needed so that we do not have to bother about the kinetic energy. When this thing moves, the pulley may rotate. So, we do not have to bother about that because the pulley is given to be massless. The system is released from state of rest, and what we are asked to find is find the velocity of block A after it has moved 2 meters. It is also given that the coefficient of friction mu k, which means it is the coefficient of kinetic friction between block A and the table, is 0.25. Block B is not in touch with the table. So, the question of friction here does not arise. So, this is the problem. Now, if we did not know the work energy principle, then we would have solved this problem by drawing a free body diagram of A, drawing the free body diagram of B, and then finding the acceleration of A and B, which would be equal. One will be in the horizontal direction, the other will be vertically downwards. So, using Newton's second law, we would have found the acceleration of block A and B, and from acceleration we would have found the velocity of the block after it has moved 2 meters, because we know that it is moving with a constant acceleration. So, from there we would integrate that to get the velocity. But if we use the work energy principle, then we are saved of this intermediate step of finding the acceleration. Because here, so when we look at this problem, what we realize is initial velocities are given as 0. The system is starting from rest, and the problem asks us to find final velocities. So, therefore, we think that possibly work energy principle would be a good way of doing this system, where we will be saved of the intermediate step of finding the acceleration. So, now when we have to do the work energy principle, what we will do is we will first mentally draw the free body diagrams of bodies A and B. So, when I draw the free body diagram of body A, what I find is the string is pulling the body A with a force, let us call this as T. And this is what we have to realize: when we have a light string which is connecting two bodies, then if the force which the string applies on both the bodies will be the same. So, if a force T is being applied to pull body A, the string will pull body B with the same force T. The force along the string stays the same. So, we have this, as long as the string is the same, the force will be the same. So, we have a string force T here on the block A. So, we are drawing the free body diagram of this block. On this block, what are the forces which are acting? A string force, its weight, and the contact forces, and the contact force will consist of a normal reaction and a friction force. So, we show all these forces. We have a string force A, we have the weight A, which we write as ma times g, we have the normal reaction which is there, let us call it as n sub A, and the block is moving forwards. So, here we have the friction force which is equal to mu k times n sub A. These are the forces acting on the body, and here what we realize is if the block, so this is friction is equal to mu k times Na. Now, because acceleration in the y direction is 0, this is our x direction, this is the y direction. Since acceleration in the y direction is equal to 0, so therefore, Na is equal to ma times g. So, the friction force is equal to mu k times ma times g, and this we can work out. This will be equal to 0.25 into 200 into 9.8. So, this works out to be equal to 490 newtons. So, now what we see is the block is moving in the x direction, there is a force T, there is a friction force F, and the block is moving in the positive x direction. So, now when we apply, if we apply the work energy principle on block A, the work energy principle tells us change in kinetic energy plus change in potential energy is equal to work done by other forces. Now, our state 1 is the state of rest, state 2 this is the final state, this is let the speed of the block be v. So, we will call this as v, and we know speed of both the blocks will be common. So, I am not putting V A or V B, they will be equal. So, state 2 the speed is given as v. Now, if we write, so therefore, now we start calculating each of these quantities. So, K 2 is equal to half m A v square, K 1 is equal to 0. So, this is for change in kinetic energy. For potential energy, both because the block is moving in a horizontal plane due to gravitational potential energy, V 1 is equal to V 2, we call this as the reference state. So, this implies change in potential energy is equal to 0. Now, work done by other forces, what are the other forces which are acting on the block? The other forces in the x direction, the block is moving in the x direction, other forces in the x direction are T minus mu k N A. So, T minus mu k times m A g, this will be the net force in the x direction. To this we have to multiply the distance moved in the x direction, we call it as S, which is equal to, in this case it has been given as after the block has moved 2 meters. So, that means S is equal to 2 meters, we say after the block has moved 2 meters. So, S is equal to 2 meters. So, this will become equal to, we worked it out, T minus 490 times 2 is equal to half m A v square. So, now there are two unknowns V and T, that is the information we will get from block 1. Then we move to the block 2, let us call this as equation number 1. Now, we move to block 2. If we draw the free body diagram of block 2, we have its weight mBg acting like this and tension T acting like this, and the block is moving down. So, this is the free body diagram of the block, and even if you do not draw the free body diagram, when you apply the work energy principle, make a mental note, you have to do this exercise. Now, the work energy principle tells us delta K plus delta V is equal to work done by other forces. Now, delta K will be equal to half mB into V square minus 0. Delta V, now potential energy, we will not talk of work done by gravity, we will talk of work done by gravity as a change in potential energy. So, this will be equal to V 2 minus V 1. Let us take the initial state as the initial state where the block was as the datum state. So, where initial state, if V 1 is equal to 0, then V 2 we know will be equal to minus mg into S is equal to minus 2 mg. So, therefore, change in potential energy will be minus 2 times mg, and work done by other forces. So, now we have T is acting upwards, this is moving down. So, work done by T on block B, this will be equal to minus T times the distance moved, which is equal to minus T times 2. So, let us write the equation for this. So, we have half mB v square minus mbg times 2 is equal to minus t times 2. Let us call this as, or let me write it as minus 2t. This is equation number 2. So, now what we will realize is, if we look at equation number 1, equation number 1 was half ma v square is equal to t minus 490 times 2. Equation number 2 is half mb vb square is equal minus mb g2 is equal to minus 2t. What we realize is 2t and minus 2t will cancel out if we add the two equations. So, we do 1 plus 2 and what we get is half ma v square plus half mb v square minus mb g times 2 is equal to minus 2 times 490. The tension component by adding these two cancels out, and now we have everything else. We have the value of ma, we have the value of mb, and we can put in all these, and when we work this out we will get the answer v is equal to 4.427 meters per second, or we can write it as 4.43 meters per second. So, now what this problem also illustrates is that if we consider A and B together as a system and we apply the principle of kinetic energy to this system, then what happens is the tension which acts on these bodies separately, but because the work done by tension on body A is equal to minus the work done by tension on body B, when we write this together as a system, the work done by T cancels out and we are just left with a change in kinetic energy plus change in potential energy of both the bodies put together is equal to work done by external forces, and T in this case happens to be an internal force whose work done cancels out. So, therefore, we just write it is equal to work done by friction and then we get our answer. But there is a bit of a catch. Sometimes work done by internal forces may not cancel out, and this would be particular because the reason is the forces which are acting may be equal and opposite, but the bodies in some cases may not move by the same distance. If they do not move by the same distance, then the work done will not cancel out. Now, there is one more thing which I would like to tell you before we wind up our discussion on the work energy principle, that the principle of conservation of energy which we have derived and which we have written as change in kinetic energy plus change in potential energy is equal to work done by other forces. And sometimes this is also referred to as principle of conservation of mechanical energy, because we are talking the principle of conservation of energy is used in the sense of when we use the first law of thermodynamics in an overall way, and so therefore, this is referred to as principle of conservation of mechanical energy. Now, from what equation have we derived this principle of conservation of mechanical energy? This has been derived from Newton's second law. So, since it has been derived from Newton's second law, for this equation to be valid, all the restrictions which hold on Newton's second law have to be valid, and the restriction on Newton's second law is that whatever velocities we calculate, velocity or displacements, they have to be calculated with respect to an inertial frame. That means, the principle of conservation of mechanical energy will be valid only if we are taking the work done and change in kinetic energy or kinetic energy etc., which are being measured are measured with respect to an inertial frame. The frame itself has zero acceleration. That means, it has to either be at rest, or if it is moving, it has to move with constant speed along a straight line, which means it is moving with a constant velocity. So, therefore, the principle of mechanical energy will be valid only if the kinetic energy and the work done are being calculated with respect to an inertial frame of reference, and this is very important. So, this is the principle of conservation of energy. Now, let us look at quantities with respect to, or the Newton's second law with respect to a quantity called momentum. We have already discussed this. We use the symbol P for linear momentum. Now, let us we define a term, we define impulse. Impulse is another vector, and we define impulse as integral f dt from t1 to t2. Now, so therefore, we see there are certain things involved in definition of an impulse. First of all, we are defining impulse of a force. So, if there is a force F acting on a particle from time t1 to t2. So, when we talk of impulse, there are three things involved. There is a force which is acting on a particle, and it is acting on a particle on a particular time interval from t1 to t2. If that is so, then impulse of a force, so what we have is actually we should be calling it as impulse of a force F during time interval from t1 to t2. So, if we call this quantity as impulse, and then this impulse is defined as integral of force with respect to time from t1 to t2. And if F is constant, in many cases we have constant forces, then impulse will be just equal to F times the time interval t2 minus t1. So, that is the definition of impulse. To see how impulse can help us in solving certain problems is, if we look at Newton's second law. Newton's second law tells us sum of external forces acting on a particle is equal to the rate of change of momentum. Sum of forces on a particle, and this is the right hand side is rate of change of linear momentum P. So, here we take the dt on the other side. So, we will get F times dt is equal to dp, and then we integrate both sides. So, we have integral F dt is equal to integral dp. Now, t let us say goes from t1 to t2, and p we say will go from at time t1 the linear momentum is equal to p1, at time t2 the linear momentum is equal to p2. So, the right hand side now is integral dp, this just becomes p2 minus p1, or this we can also write it as change in momentum. And the left hand side here is nothing but impulse of force F on the particle from t1 to t2. So, therefore, what we get is, this is what we can call as the impulse momentum principle. That impulse of a force is equal to the change in momentum, and where we know this impulse will be the integral of F times dt. So, the change in linear momentum of a particle is given by the impulse of the forces acting on the particle. Now, the principle of impulse could be useful So, this principle you will find, principle of impulse is useful if the force is a function of time. If the force is a function of time, then if we integrate this with respect to time, what we get is the change in momentum. Now, if we try to look at this, what we realize is, let us look at some salient features. The first thing we see is that impulse is a vector quantity. Now, because this is a vector equation, we can write scalar components. So, sometimes we may need only one component. So, then we write for that component, and what we will get here is the x component of impulse will be equal to the change in the x momentum of the particle, the y component of impulse will be equal to the change in y component of the linear momentum, which means this we can write it as m times the x momentum of particle in state 2 minus x momentum we can write as m times v. So, this will give us m times the change in x velocity of the particle, and this will give us m times the change in y velocity of the particle will be the impulse in the y direction. Second thing we note about impulse is, if we look at the units of impulse, so then the dimension of impulse is force is equal to m times L by t square, and we multiply it by t. So, its dimension is ml by t, and the SI units of impulse will be force is in newtons multiplied by time. So, Newton second. Now, if we are talking of a single particle, for a single particle, impulse methods are useful if force is a function of time. Then impulse just gives us the change in momentum. So, we can also write it in another way. Let us see, impulse is equal to m times for a single particle v2 minus v1, where v2 is the second state, v1 is the velocity in the first state, v2 is the velocity in that state. So, here we can write this equation as m times v2 is equal to m times v1 plus I. So, what we can say is, this is the initial momentum, and to that you add the impulse, and that will give you the final momentum. So, if you have to find the velocity in the final state, you have the initial momentum, to that just add the impulse, and that will give you the final momentum. Now, sometimes graphically this could be useful if, for example, force in a particular direction is given as a function of time, let us say like this, then area under the ft curve gives impulse. So, if graphically force is given as a function of time, you, for example, in this case the area of this triangle, if this is state 1, this is state 2, you find m times v1 plus area of the triangle will give you m times v2, where we assume force F is acting on the particle and there is no other force acting. So, therefore, then you can apply equation like this. So, this is the concept of what we call as the impulse momentum principle. Now, from here arises the principle of conservation of momentum. What we have seen is impulse is equal to change in momentum. So, therefore, if impulse is equal to 0, then change in momentum is equal to 0, which means m times v1 must be equal to m times v2. And this is what we call as conservation of linear momentum, or as we will see, there is another momentum we will define. So, this is referred to as conservation of linear momentum. Now, for a single particle, if we look at this concept of conservation of momentum is not very useful, because it is very obvious if no external force is acting, then the momentum of the particle does not change. So, if there is only one particle involved, in the impulse principle may be useful if force is given as a function of time, we integrate that to find the final momentum. But if impulse is 0, the conservation of momentum principle for a single particle, the law is not very useful. The conservation of momentum principle so if we write the conservation of momentum principle, this is useful if we have more than one particles involved. So, then as we have seen the example for energy which we saw, there were two blocks, and if we consider both of them together as a system, there are cases like that where we have two particles which are there, and in there if these two particles are interacting, then the principle of conservation of momentum can be useful, and we will see how it is done. But for that to be useful, what we need is Newton's third law, which tells us the forces between these particles are equal and opposite. So, when we consider both these particles together as a system, then the internal forces between them will not matter, they will cancel out, and we will just talk of external forces acting on the total system. But before we do that, we introduce another concept. We introduce a concept of instantaneous impulse. And instantaneous impulse means if a very large force acts on a particle for a very small time, then the impulse of this force is said to be an instantaneous impulse, and this force sometimes is referred to as an impulsive force. So, now let us just try to see mathematically what this means. So, what we are now defining is, we have already defined this quantity impulse, let us say INST, which shows an instantaneous impulse. This will be integral from T1 to T1 plus epsilon of integral f dt, where when we take the limit, epsilon tends to be 0 and f tends to be very large, which means we can idealize it to be going to infinity, and if the average value is of this force is f average, which is large, and we are multiplying it by T1 into T1 plus epsilon, which is basically epsilon, this delta t is nothing but epsilon, which is very small. So, this product is like something like infinity being multiplied by 0, this will be a finite product, and this is what we call as an impulsive force, and the impulse due to this force is what we call as an instantaneous impulse. Is this just a theoretical concept or is it a practical concept? And let us give a couple of examples, both of which are very similar. The first one, let us take the case of Roger Federer hitting a tennis ball. Let us say Nadal is serving, the ball comes and Federer hits the ball with his racket. Now, the time of contact between the ball and the racket is very small, and the contact force is very large. So, such a force is an example of an impulsive force. A force which acts for a very small time, but the force is very large. And what is the effect of this force? Let us see. The ball is coming from this side till it hits the racket, and so when the ball is coming, it is coming with some momentum, and the racket applies a force on the ball, and what is the net effect of that? So, this force plus the impulse will be equal to the final momentum, and the final momentum is nothing but the final velocity of the ball multiplied by its mass. So, therefore, whatever force Federer applies on the ball with his racket is what gives the new velocity to the ball, and it has a twin effect. First effect is it is coming in an opposite direction, first it stops it and then it makes it go with a very high velocity on the other side. And so, this contact period and this contact force is what we are calling as an impulsive force, and the impulse is what we are calling as an instantaneous impulse. And a second example of this could be a very similar example when Virat Kohli hits the cricket ball with his bat. Once again, the ball is coming, the bat changes its direction, bat applies a force because of which the ball changes its direction. So, what we see is the effect of the impulsive force is one, the direction of the particle could be changed, and secondly, the speed of the particle is also changed. So, either one or both of these effects could take place, and this is what the impulsive force or any force would do on the particle. Now, when an impulsive force acts, on a particle, other finite forces may also be acting during this interval. When an impulsive force acts, it is possible other forces are also acting. For example, when the tennis ball is coming and is being hit by the racket, gravity is also acting during this time, but because the impulsive force is very large and this force is acting from T1 to T1 plus epsilon, a very small period of time. So, during this time period epsilon, we neglect the effect of the other finite forces. Notice the effect of these other finite forces is only being neglected during the time period epsilon. Before time T1, the trajectory of the ball is governed by the finite forces, for example, the gravity acting on the ball. And after the time period T1 plus epsilon, once again the impulsive force is not acting. So, the motion of the ball will be governed by its initial state and also of the finite forces. But during this interval, while the finite forces act, we neglect their effect. And this graphically we can show very easily. Suppose if we draw force versus time, let us say this is gravity force which is acting on the ball, there is some other finite force, it may be some other force which is of the same order, and the impulsive force which is acting, it will be 0 up till time t1, and at time t1 a very large force acts and it stops. So, this time is t1 plus epsilon. So, what we are saying is during this time period from t1 to t1 plus epsilon, only the effect of the impulsive force is counted. We do not count the other effect, and this is very clear that if we look at the change in momentum, it is due to impulse. So, this area will be much larger during this interval epsilon than the areas by gravity and all, and as epsilon goes to 0, these other force, the impulse will go to 0. So, therefore, we just use this. Now, sometimes in the problem you are asked to find the average contact force, F average, and if the time of contact is given as delta t. So, then what we have is F average times delta t. Now, when we talk of F average, that means what we are saying is this average force is acting over the entire period delta t. So, we treat F as a constant, and this must be equal to the change in momentum. So, if we know P1 the initial momentum and the final momentum P2, this P1 just to recall is mv1, this is mv2. So, if we know these, then we can find the average force. So, if you want to find how much force does Kohli's bat apply on the ball, for that you need to know the initial momentum of the ball, the final momentum of the ball just after he has hit the shot, and the difference of these two will tell you how much force. And if you have an estimate of the time of contact during which the time for which the ball has been in contact, then you can find the total force. Okay. So, now let us see how this principle of momentum can be used when we have more than one particle. And this is what we said, that this is where we will have the, we could possibly use not the impulse principle, but the principle of conservation of momentum. Now, what are the type of problems where we will have more than one particle where such things could work out? One of the very typical problems which we have are what we term as collision problems. That means we have a body of mass m1 travelling with a velocity v1, and we have a body of mass m2 travelling with a velocity v2. These two, this is what we can call as the pre-collision stage. They touch each other. So, this is at a velocity v1, this is at a velocity v2. They hit each other, and this is what we will call as the collision stage. And after they have hit each other, this goes with v2 prime, this goes with v1 prime. These are the final states, and this is what we can call as the post collision. So, this could be one state where we have more than one particles involved. The second type of problem is when we have one body which is moving and it suddenly breaks into two or more parts. So, it is something like a splinter which is moving and then it breaks into two parts. So, this is ma, and this breaks into two parts B and C. Now, this breaking up will be because of internal forces, and then we can let us see how we can apply principle of conservation of momentum. Now, in these, if we treat, so that means we have more than one particle. If we treat both the particles, so let us take a case of two particles, and we treat both the particles as one system. And let me first state the principle. If no external force acts on the two particles, then the momentum of the two particles as a system is conserved. So, first I have stated this principle. If no external force acts on the two particles, now by external force, force which is external to 1 and 2. So, we will just show how this works, but the principle says then the momentum of both these particles together as a system is conserved. So, let us say we have a particle A and on which an external force F A is acting, and we have a particle B on which a force F B is acting, and these particles may be they interact with each other. So, let me show them close to each other, and maybe they are hitting. On this external force F A is acting, on particle B force F B is acting. Now, if I draw the free body diagram of particle A, then free body diagram of particle A will show me F A. Now, I have to show all forces external to particle A. Now, particle B, suppose these are touching each other, will exert a force on particle A, and let me call this as F A B. This is the force exerted on particle A by particle B. Now, let me also now draw the free body diagram of B. Free body diagram of B shows the force F B, and then on this I will have F B A. This is the force exerted on B by particle A. Now, when we add up the two systems, and what do I mean by adding up the two systems is, let us add up the forces acting on the two systems, because we are considering both of these systems together. Then what will happen is, we realize we have Newton's third law which is there, and Newton's third law tells me F A B is equal to minus of F B A. So, the internal forces which exist among these two particles, they will cancel out. So, now let us write the impulse momentum principle. So, what we will have is the impulse momentum principle for particle A, that will tell us integral F A dt plus integral F A B dt is equal to change in momentum of particle A, and impulse momentum principle for particle B gives me integral F B dt plus integral F B A dt is equal to change in momentum of particle B, and when we add these two, what we will get is integral Fa plus Fb dt plus 0 is equal to change in momentum of particle A plus change in momentum of particle B. And if, so this is the total impulse momentum principle applied to each particle and added up, and if Fa and Fb both are equal to 0. This is what we said in the law of conservation of momentum, that external forces to the system. Now, we have particle A and B. External forces to the system are Fa and Fb. Now, these could be because of any external things. If this is equal to 0, then if Fa plus Fb is equal to 0, so if these forces are equal to 0, then the change in momentum of particle A plus change in momentum of particle B is equal to 0, and this I can write it as Ma Va plus Mb Vb at state 1 is equal to Ma Va plus Mb Vb at state 2, and this is what we call as the law of conservation of momentum. And this, as we said, this could be used if we have impact problems, collision problems, then if external forces are 0, then we can use this. And as we have seen, in some cases external forces may not be 0, but in a collision, let us say when we talk of a collision problem, during the collision period, the collision forces are much bigger than the other finite forces. So, for the period of collision, since if both particles treated as a system, then during this interval, if both the particles are treated as a system, then the momentum of the system is conserved. That is, we get the initial momentum is equal to the final momentum. So, this was the principle of conservation of linear momentum. Let us now also define another quantity which we will call as angular momentum or moment of momentum. And let us define this. If we have a point O, so there is a point O which is fixed, and we have a particle moving with a velocity v which is at this position p. So, here now if we write O is a fixed point, the particle is moving along some path, its current position is given by p. So, if the position vector of the particle, which we write as OP, and let us write it as R, or I could even call it RO, which means it is R with respect to O, which is a fixed point. Then we define angular momentum, or we will also call it as moment of momentum of the particle about point O. Now, this is important. Angular momentum is always about some point, and this we will define it as the vector r cross with mv. This is the linear momentum or the momentum, and whenever we cross a quantity with r, we call it as moment of that quantity. So, r cross mv is called the moment of momentum or linear momentum, and we use the symbol capital H, and O represents it is moment of momentum about point O. So, this is how we define angular momentum of a particle. So, let us say if a particle is moving along this path, this is a point O, let us say this is one position. So, we draw a position vector at this position 1 and its velocity is like this. Now, this need not be perpendicular to each other, they may be perpendicular if it is a circular path about O. So, then if this is V at position 1, so H about O at position 1 will be equal to, let me call this as R1 cross M times V1. Similarly, at this position, if the vector is R2, the velocity here is V2, and then we have angular momentum at this position 2 will be equal to R2 cross M times V2. So, this is the definition of angular momentum. Now, what we realize is angular momentum, once again this is a vector and we define it as R cross mv. So, that means it is perpendicular to R and it is perpendicular to V because it is a cross product. So, this is how the angular momentum goes. Now, let us look at this quantity. So, we have defined H0 is equal to R cross mv, where R is the position vector of the point from a fixed point. Now, let us define this quantity. Let us take a derivative with respect to time of both sides. So, this will become d by dt of R cross mv. This we can write it as dr by dt cross mv plus R cross, assuming m is a constant, m times dv by dt. When we are writing for a particle, obviously mass can be taken as constant, can be taken as a constant. Now, dr by dt is nothing but the velocity vector. The change in position vector with respect to time from a fixed origin is the velocity. So, this first term becomes v cross m times v. So, therefore, this becomes equal to 0 and this becomes equal to the second term becomes r cross m times dv by dt is nothing but a. So, therefore, this becomes equal to a. So, what we get is dho by dt is equal to r cross ma. And if we are measuring things in an inertial frame of reference, m times a can be written as the external force on the particle. So, let us write it as F. So, therefore, what we get is dho by dt, rate of change of angular momentum, is equal to r cross F. So, if a force F is acting on the particle, it's the rate of change of angular momentum will be given as r cross F. And this is, as we will see when we do rotational mechanics, this is also written as moment of the force about point O. Just as we have written moment of momentum, r cross F is called the moment of the force. So, therefore, we have this moment of the force, and so this we can write. Therefore, if moment of a force can be written as m sub O, what we have got is dho by dt, rate of change of angular momentum, is equal to m sub O. And if moment about O is equal to 0, this leads to a condition that dho by dt is equal to 0, which implies ho is equal to constant and h is the angular momentum. So, therefore, this gives us, if we are talking of two states 1 and state 2, h about O at state 1 is equal to h about O at state 2, and this is what we can call as the law of conservation of angular momentum. So, this is law of conservation of angular momentum, and for this law to be valid, what we are saying is, if moment about O is equal to 0, then H about O is conserved. And the place where this becomes particularly useful is when we talk of planetary motion. When we talk of motion of a satellite about a planet or motion of planet around a sun, then the force acting on the satellite is just the gravitational force, which is given as minus g times m1 m2 upon r squared, if this is distance r, and it acts towards the center of the planet. So, if we call the center of the planet as O, then what we will realize is that for the motion of satellite, about the planet, its angular momentum about O will be constant. So, in problems like this, if we have a force which is always acting towards a point O, then the particle is under the motion of a force. So, if particle is under the motion of a force which always points towards a fixed point O, and this is the only force on the particle, then r cross mv at position 1 will be equal to r cross mv at position 2 for the particle, where and r is the position vector with respect to O. So, this is the law of conservation of angular momentum for a single particle. So, today we have seen the principle of conservation of linear momentum and principle of conservation of angular momentum. In the next class, we will specifically look at the collision problem, where two particles come and collide and then they move away. How do we solve problem like this? How do we apply the conservation of momentum? Is that enough, or do we need something else?